Hi. So I think part of the idea with these is to give a couple minutes on sort of where I've come from. So I'm going to do a little bit of that. I think, as was just mentioned, funnily enough, I went to school with this guy right here. We were in this sort of same dorm at University of Toronto, just a couple doors down. And I guess I feel like now, looking back, we definitely didn't know it at the time, but we were insanely lucky. So we basically landed at a school so this is University of Toronto, and Jeff Hinton was teaching the neural nets course there. So we just like it was just like incredible luck. And we both were doing a CogSci AI program, which was great in general, but then in particular, I took the neural networks course in computer science, and basically was like, well, this is it. Which is easy, like when you have Jeff as a teacher, like he's pretty compelling for obvious reasons, and that really got me interested in like, hey, these things maybe are going to be pretty important models for brains. Interestingly, at the time, I think it's worth saying, when I then switched and went into from my undergrad, went in to do sort of master's and PhD work, in neuroscience, neural networks and backpropagation, these were pretty dirty words and people were, I think, pretty unhappy. Like the idea was these were black box models. This is not what we do in neuroscience. This is not how we do neuroscience. These are not going to tell us much about brains. And so there was definitely like a funny a funny set of years where that was sort of the general feeling. Not that you couldn't find corners where people were like excited by these models, but there was a general tenor in the field that this is not what we were going to do in neuroscience. This is not how we were going to really understand brains. I then actually went and did a bunch of wet work in my postdoc, which I loved. And actually, I don't know how much wet work is in this building. Maybe not. I don't know how much. Like mix, yeah, fair amount. And actually, I loved wet work. It was really fun, like working with my hands. And at the same time, the pace of it was a little bit slow for me. Like it was sort of like the 1 year to get your experiment, to get all your data for your experiment was a little bit slow. And so I think I just like got increasingly excited about the computational stuff I was running on the side, and got pulled in by. So at that point, there's more. Actually, I had more luck than I even remember. At that point. Ilya Sutskever, who was the chief scientist at OpenAI for a good chunk of time, also went to undergrad basically sort of concurrently with us. So he was there at U of T. And at that point, I sort of had kept in touch with him from sort of my PhD. And he sort of said, hey, like there's kind of this crazy stuff going on in industry where people are really working on some of these things at places like Google. Why don't you come check out this thing called DeepMind? And I did. And to be frank, actually, when I went to visit industry, it was weird. Like I had assumed I'm definitely just going to go and try and be a prof and make a run at that. And that was my sort of default assumption. And this idea that you take an industry job and try and publish was like frankly kind of scary, and actually took a leap of faith that like this was maybe a sane thing to do for an academic career. And it has worked out okay, but it was a strange time, and I think it probably is still a strange time. Anyway, since then, I think it maybe, I don't want to eat too much of the actual talk content, so that's sort of maybe a setup, and we'll talk about it. But obviously, since then, AI has gone kind of nutty, and we'll talk about a bit of that in the course of this talk. Yeah. The other thing I wanted to say is please just like questions as we go. I think that this is a fairly broad audience. Actually, to take one signal or two questions. How many people have implemented backprop by hand, like themselves? Okay, so it's like maybe like a quarter, maybe. And then how many people have implemented a policy gradient algorithm? Okay, so like 3. All right. Okay, so this is good. It's good for me to take that temperature, and I'm gonna try. So I do want questions. Like try and hit me with them. I'm gonna try and like just bring the stuff to where is appropriate. So, but just hit me with questions. So I'm gonna talk about learning to think by reinforcing useful thoughts. What am I gonna try and do? What I'm going to aim to do is I'm going to try and tell you about some of the recently developed models that learn to think and the algorithms that underpin them. I'm going to try and get at the general principles and connections to what's called model-based reinforcement learning, which is where I spend a lot of my time, and some of the earlier work in game playing and sort of allusions to learning in humans. In particular, when I say these models that learn to think, when you interact with the chatbots today, they have a bunch of this going on behind the scenes. So they have a bunch of sort of, in some sense, thinking that's going on behind the scenes. We can talk about, like, is that word appropriate and so on, but there's some sense in which they're spending time and effort to produce better answers. Where are we now? So we just to very quickly paint the picture on some of these language models, chatbots. We trained language models on a bunch of internet text, and this let us build chatbots with some pretty amazing properties. And sometimes they're useful. And then really, I would say over the last 12 months, there's been a wave of much, much better performing chatbots. I don't know how much you've used them, but if you sort of use them in the early days versus the last 12 months, there's been a massive improvement. And that improvement in the sort of last 12 months has largely been driven by reinforcement learning, which is what I'm going to talk about today. And that's really what's enabled these things to think to an extent. I want to talk about this a little bit, especially for a sort of a general crowd. Where are we headed? I think we're at a funny moment, like in history, and it's worth sort of taking some of that on board. And what I'm going to try and do through the rest of the talk is just connect some of the technical pieces to this. But I think we're something like 5 to 10 years away from models that really are pretty good at almost all digital tasks. I think the real world is like a whole nother business, and I feel like there's many, many more questions there. Robots are a mess. Material science is really hard. It's hard to build things that don't break, et cetera, et cetera. But when we talk about digital tasks, I think we're going to have remarkably capable agents. And this is something that we kind of need to all grapple with. And I think nobody will, 10 years from now, will have escaped this, including machine learning researchers, right? So this is something I think we need to all take seriously as people who think and write and read for livings. There'll be all kinds of things that I think may be untouched. There's all kinds of things you could say about this. I don't want to dwell on it too much, but I do want to load this a bit in our head as we head into some of the technical pieces. And I think partly I want to convey, I think there's a lot of questions out there about, have we hit peak AI? Is it going to level off? These kinds of things. And partly what I'm going to try and arm you with is some of the technical ideas from reinforcement learning side, to sort of expect that indeed, I think we'll continue to see pretty rapid progress in the next 5 to 10 years. And just have some of those sort of technical pieces. Okay, so here we go. What do I mean by learning to think? So really, because I'm talking about these models that have gotten better at performing, and specifically I'm saying they've gotten better because they do something like thinking. And by thinking, I really just mean the capacity to spend more time and compute for better answers to a question. And at the same time, models need to learn this capacity from feedback. I think we found that's sort of critical. This is sort of the quintessential example, right? Someone's sitting at a Go board, and literally, one of the things that chess players learn is how much time and effort to spend on particular moves. And they really spend time sitting there, ruminating to produce a better answer to the current situation. And this is what I mean by thinking in some very generic sense. The extent to which, the current models map onto what humans are doing, the very tenuous, loose connections. But at this very high level, computational level, I think that there's a deep connection. Yeah. Okay, so then I guess a very brief sort of opinionated history of some of the things that happened with models over the last sort of 10 years. There was a bunch of work using our reinforcement learning for games, and some of these things I was a part of in various ways. Then we had these pre-trained models show up from OpenAI that really sort of took the world by surprise. And then instruction-tuned versions, which I would say were sort of the first variants of these things, which were a bit more useful, like kind of not just something that was interesting, but a bit more useful, like you could maybe get something out of them that was useful. And then it's really since about this period where there's been models that I would say have really started to do things like be a bit better on hallucinations, to actually be able to do mathematical tasks, to be able to do tasks like coding. And so that's sort of where we started maybe 12 and a bit months ago. And that's what I'm going to talk about primarily. So to give you a sense of what that looks like in terms of this transition from the sort of instruction-tuned things to really sort of performing reinforcement learning with thinking, these are sort of some of the numbers that sort of happened within a very short amount of time. So you had models that were sitting here. This is one benchmark on math, and they were sort of producing maybe 35% performance. And in the span of about 6 months, when this started taking off, you saw about a 40% jump in some of the performance of these tasks, really kind of quite wild. And I think this was fundamentally because these models went from, oh, I'm just trying to do pattern matching, like you gave me a question, and I'm going to just try and pattern match to an answer, to a model that was sitting there getting a question, like trying to think a bunch, and then produce an answer. And and actually directing reinforcement learning to do that and try and do that better. Okay, yeah, please, as I said, I'm moving pretty quickly because we're going to hit a little bit of technical stuff, but I definitely want questions as we go, so if there's anything that's confusing, let me know. And so I think this was, why do I think that things are going to continue to move quickly? I think that's what the why was referring to here. Reinforcement learning is starting to work for these large pre-trained models, giving them some capacity to think. I think we have more and more evidence that reinforcement learning can be extremely efficient when you have a pre-trained model that sort of knows stuff about the patterns out there. So that is, whereas we've had this sort of sense that you need tons and tons of data, billions or even trillions of tokens to train one of these pre-trained models, we're starting to see that for reinforcement learning, potentially with 100 questions or data points, you can learn something substantively new using those models plus reinforcement learning. I think we're also increasingly being able to teach models in some sense in the way that we teach humans, speeding up learning processes. So one of the things that people are actually starting to do is to give models hints. So you'd say like, here's a math problem, try, okay, I can't do it. So you say, here's a math problem, here's a textbook as well that's sort of relevant, that has some of the relevant information in it. Like take a look in there, see if you can find anything that's useful to apply here. And so like this idea that you could sort of begin to produce hints and prompts for models is becoming possible. And the other piece that's really pushing into this is that models are now, I think, reaching the point where they're improving research velocity itself. So people are really starting to take the models, like they're actually good enough that you can go and sort of point them at things like data filtering tasks, data extraction tasks, things like this, which actually speed up the research itself. So all these pieces, I think, are coming together, and I'm going to tell you a lot, mostly about how this RL works and some of the background that went into it. Okay, so this is the kind of the picture for reinforcement learning, and we'll unpack tons of this as we go. But this is what we have in mind, right? So you have some big neural network, or maybe it's a small one back in the day. It basically takes some inputs, which is an observation of the environment, and then produces a probability distribution over actions. And then you're going to sample an action. So you're going to sample an action from those possibilities, send it to the environment. The environment is going to say, given where I am in the environment and an action, I'm going to sort of process to the next state. And then the agent gets that and also gets a reward. And so the two things that I'll have in mind throughout are like maybe the chess example, where this is the board state. That's the state of the board. These actions are playing a move on the board. And then the reward is, did you win, lose, or tie the game? So that's the chess case. And then on the machine, the sort of the case that we're all familiar with in our day-to-day use of chatbots mode, it's like the environment It's a little bit stranger. It's like the prompt, so it's like something you said, the question you asked. And then the environment, weirdly enough, for these agents that learn to think, is going to be sort of like self-production of tokens. So when you produce these actions, they almost sort of become part of the environment. So you're actually rolling out thoughts in your head, tokens in your head. And then the response as well are actions, are also actions. Anyway, we'll sort of unpick this as we go. But those are the two things to connect to. So then maybe starting the chess case, because it's a little easier, you can think about what a single trial of reinforcement learning looks like. You start at, say, some empty board. You produce a probability distribution over the actions you take. You sample an action from that distribution. You get a reward. You go to the next time step. You advance the board state. You sample an action. You get a reward, and so on until the end of the game. In chess, the rewards at each time step are basically 0, and then it's only at the final time step where the game ends that you get a reward of like -1, 0, or 1, and that's whether you won or lost here. You can express, and this is maybe not too important for this for us, but you can talk about the probability of a particular trajectory tau given this expression. It's not too important, but the idea is you can sort of think about a probability through chess games, right? Or through the response to a question that was input to a chatbot. Okay, so then you sort of say, like, what do we care about in reinforcement learning? We really care about this thing called the return, which is often the sum of rewards discounted through time. So you're basically sort of saying, like, I have this episode, and then what I want to do is I want to maximize the reward that I get as I move through those states. And then finally, what I then really care about is this objective function. And actually, I'm going to do one thing, which is just to flip back for a moment, which is, and note that usually we parameterize, there's the weights in this neural network. And those I'm often going to call theta. Those are just the parameters of the neural network, like the weights in it, that I can adjust and change so that the probability distribution is shifted. So then what I say, like, what I really want is to maximize the return. And so that's for the return for a single trajectory, tau. So then if you think about it, what I really want to do is change the weights in the network, that's theta, so that this integral is maximized. And this integral says over all trajectories, so it's basically an integral over all the possible trajectories that you could take. I get a return for that trajectory, so that's the final return I get for that trajectory. And then this is the probability that I will take that trajectory given my theta, which is given like the parameters of my neural network, right? And so this is kind of the full thing, and I want to make that bigger. I want to make that better. And so that's, in some sense, what I've spent a lot of my career doing in various forms. And so there's this lovely idea called the policy gradient, which I asked you guys about, and I'm going to spend a moment trying to explain this. I think there's a very intuitive. There's a lot you can say about this and a bunch of math, but there's a very intuitive idea here, which I think we can all latch onto and get your heads around quite quickly. And so it basically looks something like this. So this is basically saying the gradient, the policy gradient of this thing, this is the thing I want to make bigger. And the gradient with respect to theta, which is the parameters of the network, so this is like how should I change the network to make this bigger, it's equal to this expression. And basically, this expression is talking about the log probability of the action given the board state. Let's keep it in chess circumstances. And this is effectively saying, look, when this thing is big, when the return is big, so imagine you won the game. So if you won the game, what we're going to do is increase the probability of these actions that were taken by the network. And that's what this policy gradient is saying. So in some very, very simple, dumb sense, it's saying, if you win games, if you get lots of reward, increase the probability of the actions that you took when you played that particular game. And vice versa. If you had negative rewards here, you would sort of decrease those. Yeah. Cool. Maybe someone who's like not super familiar with this stuff want to ask a question. Just one, it would be great. Because I think, like, look, there's probably, given the number of people who said, there we go, great.
I'm ignorant to that. If I had an unsolved problem, I don't have the learning from winning, but I want to know if I'm getting closer to being able to make the jump. You must deal with that a lot.
Yeah, good. Okay, so you're saying, I think, like, yeah. Okay, so there's lots of ways I could come at that question. I will take one crack at it, and then we'll see. I'm going to get so this in this sort of rollout through time, right? So this is through time. In chess, I only get this reward at the final time, right? And so like there's all these intermediate states that you get into, and most people who've played a board game know that like, okay, well, there's winning and losing, which is what I really care about. But midway through the game, it can be very apparent to you that effectively you've already lost, right? And so in chess, in some sense, the way we represent this in reinforcement learning is that the reward here is always 0 until the very final time step. But somehow humans absolutely know that, like, 5 moves in, someone's playing very well and I'm in a bad spot. I know that and I can learn from that. So absolutely, what humans and people are doing is building up some model of reward even before you have those kinds of things. And I'm going to talk about that explicitly in the form of value functions, which I'm not sure but anyway, yes. Okay, great. So fantastic question. Did that kind of address your question or get at it at all?
Good enough.
Good enough. Okay, it was one slant. Good. Okay, so then here is kind of, this is kind of, I guess, an encapsulation of a lot of the work I've done, and in some sense, weirdly, this single slide encapsulates a lot of what's gone on in the last 12 months for some of these large language models in a very ridiculously simplified way. But this really captures it, which is you'll basically do a rollout. So that's roll out one of these trajectories, and so by that I mean you like stick in this question, a math question. You let the model produce a bunch of tokens internally, and then produce some tokens which are part of the response, the actual answer. That's the trajectory, or this is a chess game. And then I basically just say, okay, I compute an estimate of the policy gradient, which tells me what direction to move the weights of the neural network in using this policy gradient. And then I'm just going to make a small update. Theta I plus 1 equals this plus a small policy gradient update. And I'm just going to step the weights a small amount in that direction, and that's it, right? And this is basically what's driven a huge amount of work, including in some of the recent language models. Good. Okay. Value functions. So one of the things I'm going to try and talk to you guys a bit today about is models of the world, and like this being, so I guess I should say these policy gradients are great, they function, but they're certainly not everything, and in order to learn quickly, you really want models of the world. And one of the most basic models of the world you can have is a model of future value, and that's what we call a value function. So I'm going to tell you how this sucker works. Basically this says this value function, which is about pi, so your current policy, how it operates, is basically it basically says, if I started at this time step in this state, so if I started in this board position, and then I did lots of rollouts, so basically I sampled many times from the policy till the end, what is the expected reward that I would get? So like, what's my probability of winning in chess would be the idea, basically. And so this is a model of expected reward into the future based on given the policy I have now. So if you like, this is the sort of thing you could compute at every time step. So it basically says, I'm at some board position which is in the middle of the game, and this thing will kind of say, if I had this function, this thing will say, what's my probability of winning right now? And I can use that to do a better version of the policy gradient, which I'm going to talk about in a moment. So here it is. And this it's kind of interesting. This stuff is complicated, but at the same time, like most folks here, I think, can get their head around most of what's in this slide pretty quickly, and it captures a huge amount of what goes on in a lot of these cases conceptually. So now we're going to talk about this simple, it's called model free. This maybe is a bad nomenclature for the field because actually there is a model here, it's a value function model. Now I have this slightly more complicated network where I have a policy, as I did before, parameterized by theta, and that's the thing that's going to act. But then I also have this model V, which tries to predict this value that we talked about. And so basically, we have two loss functions now, two ways that we update this network. The first one is basically a loss function which is telling us how to update phi, the value function. And it's basically saying, I have a return, and I have a value, and I'm going to compare these suckers, and I want this to be small. And if they were small, that would mean that the value function is doing a good job of predicting what the outcome of the game will be, right? Like if it's good at predicting, like that will basically be 0. So that's how you train the value function, is you basically tell it, like, try and drive that error to 0. And then in the policy gradient, previously it was basically just saying, I'm going to adjust the probability of this action, the log probability of this action, based on the return. So based on whether the return was high or low. That's previously what I did. Now what I'm doing is I'm going to adjust it based on the difference between the outcome of the game and what I expected the outcome of the game to be. And because this value function can be applied at every state, at every time step, I can do it at every time. I can apply this like at every moment, at every time. I don't have to wait till the end of the game in order to be able to sort of make these updates and to have a, yeah. And the other thing to say is that doing this typically, if you have a good representation, a good estimate of the value function, this is a lower variance estimator for the policy gradient, which basically just means that your learning updates will be better and quicker. That's the short version.
What is big R sub t?
Big R sub t. Big R sub t, yeah, so good. That is probably some terrible nomenclature on my part, where this is this is supposed to be, it should probably here just be R, yeah. So yeah, yeah.
But doesn't that overcount? Because V phi st is not just this reward from this episode period, but all of the future, right?
That's
but
right.
R sub t is just from this particular.
That's right. And so, yeah, sorry, I think that the t should not be there. This is like trying to predict the return of the episode. Yeah, so like imagine the t is not there on the R. Anyway, I think there's reasons. Yeah. Was there another question?
So your policy does not depend on the value function explicitly. This would be in some.
That's right. Here, the policy does not depend on the value function explicitly, although, as we'll see, that's not always the case. Yes. You can use the value function in the policy itself. That's right. Yeah. Okay, so I guess a punchline here, and part of where we're, yep.
Sorry, I'm just going to ask, so that's updating like during the game, but then how do you start the game? Because like in a chess game, you can move a bunch of different pawns ultimately at the start of the game to get to the same outcome, which would be to win the game. So then how do you account for like the first decision?
How do you account for the first decision?
Is it a matter of probabilities? Is it like, oh, I have to move one pawn because this pawn is my go-to pawn? Or is it, oh, I have a bunch of different paths I can take?
So I guess, yeah, okay, good. It's good to just drill into a couple of these. Like literally on that first move, you've got this policy function. You would put in like the sort of opening board state, and there's some probability distribution here. And if you're learning from scratch, where the probability, like the policy function is just random weights in the neural network, you'll basically take a random move, and that's how you would start, right? It'll literally be a random move, and to the extent that these things then develop like, really like hone in on like this is the move that I like opening with. If you're learning well, it's because that move is effective and is generating better returns for you. Yeah. Good. Okay. So these poorly named model-free algorithms, and we'll talk about what people then mean by model-based a little bit. They tend to work, but they're pretty slow. So this was like in 2016, we sort of began applying, actually just like that last slide, to playing video games. And this was an agent that learned, it was initially random, but it learned to like process around this like very simple video game world and pick up these apples. At the time, this was like kind of crazy to us that you could do this and make it work all from images. But this was huge amounts of data. So this was training step in the millions. So this was seeing millions and millions of frames of data in this tiny world to get to the point of being able to do this. So these things are effective, but they're very slow. And there's a couple ways that people have overcome this slowness of reinforcement learning. One of the main ones that I'll talk about is combining networks with models of the environment and planning. And this, I think, I'm going to try and connect to a lot of what's going on in the chatbot space right now. So in effect, I think a lot of what we've seen in terms of like this thinking behaviors, this sort of planning behaviors, we've had in games for a while. And what we're seeing is sort of new variants of that in the chatbot space. So what's happening here? In the Go case, we can actually use an environment, use a model of the environment, like a sort of a perfect one, to plan and do things. And I'll talk a little bit about what I mean by that. But in effect, we could kind of say, look, for chess, I could have an exact simulator of how chess works in my head, and I can make it, and I can use it to play better. I can use it to do better reinforcement learning. And this is basically how this works. We're still going to build a policy network. So this was for the case of learning to play Go. We're still going to build a policy network. So this is one of the reasons I wanted to bring like some of these concepts up, is that they're just going to come up over and over again. It'll become hopefully almost sort of fluent. We'll also build a value function network, which is saying, in this board position, what's my probability of winning? And then to do that, just to say, where did those come from in the original AlphaGo case? What we did is we took human expert positions and we trained those networks. We trained these networks to predict the next move played by humans. So actually, this has a very clear analogy to what's going on in the chatbot space, which is go and get a bunch of data from the internet, and instead of predicting the next move, we now predict the next token of language, right? So this was like a very, very close analogy. Once you have this network, you can then go and do a bunch of self-play, where you literally take the network and have it play games against itself and generate a bunch of games. So just like literally have it play out games. Once you've got those self-play positions, you can do regression and produce a value function network. So basically one that looks at those board positions and predicts the outcome for that policy. Once you've got that, I'm not going to get into all the details here, but I'm going to build the picture for you quickly. Once you've got that and you have a simulator for the game, so once you've got a policy function and a value function and a simulator for the game, you can then do something called Monte Carlo tree search, which is a type of planning. And so in effect, I think we all have some model of this. You can sit there at some board position and you can sort of say, I can imagine futures that might happen. Like I play this move, then my opponent plays this move, then I play this move. Or I could go this way and play this move, and they play this move, et cetera, right? So you're going to build up this tree of possible games that are played and possible outcomes that are reached. Importantly, when you build that tree, and this is why you need this policy function and value function, like chess is just way too vast. Like you can't build the whole tree. It's completely mad to do that. So what you do is you use the policy function to do things like expansion, which is basically saying, like, look, the policy says that these 5 moves are promising. So what I'm going to do is I'm going to expand the tree to those 5 moves, say, that are promising under the probability distribution of the policy. It says those 5 are good to try. Good, I'll do that in my head. And then when I get to the bottom, I'm actually going to take the board state, put it into my value function, and that tells me, even before I get to the end of the game in my head, that's how promising I think this state is, right? And then you can basically do a phase called backup, where you sort of back up those values. and you sort of say, oh, this is the guy, this is the board state that the sort of subsequent evaluations of board states, this is the one that looks really promising, and I'm going to double down on, and ultimately maybe I'll even choose it as my action, right? So basic, yes, please.
So
Yep.
when you said taking longer to think, and now GPT says taking longer to think, is it kind of saying what they're doing?
Yeah. Okay. Well, so is it? Yeah. That. Okay. Great. So this is exactly the sort of connection to make. Is it exactly MCTS? Well, first of all, we don't know because there's some proprietary secrets. Probably from what we can gather in the literature, it's unlikely to be exactly MCTS, and there's probably lots of reasons we can get into that. But the fundamental idea that what you're doing, what's going on behind the scenes, is that you're spending a bunch of time. So in particular, you can imagine building this tree bigger and bigger and trying more and more things and backing up and getting a sense of like, oh, this looks really promising. Now I'm going to spend even more time thinking over here. This is what's going on in some sense behind the scenes. That's right. And so the MCTS is like one of the first instances where we really saw a breakthrough of combining these classical planning algorithms like MCTS with neural networks, putting them together productively. Yeah, but there's a lot you can do with it. Great question. Yeah.
Sorry, I'm having a bit of trouble even at like a super high level of
Please.
what the
Yeah.
model is.
Yeah.
So it sounds like when you say simulator, that's synonymous with model. Is that fair?
Yeah, so in this case, when I say simulator, I mean literally that we have, like you have a chess engine, and you can sort of say, from this position, there's certain legal moves that are allowed, and I could play this move, and it would give me this consequence on the board, or I could play this move, and it would give me this consequence on the board. And so part of building up the tree in your head is literally like using the simulator. I'm gonna talk about relaxing this in a moment because like obviously for most things that we care about as humans and even like that we ask chatbots about, there's no perfect simulator, right? So chess has the luxury of having perfect simulators and like you just don't have that most of the time and you need to relax it.
Is there any way to have like an intuition, like at any given state or any given time step, what a model-based versus a model-free decision looks like?
That's a good question. The answer is probably messy. So we'll let's chat about it after if you're curious. It gets into the weeds. Some of this is like silly semantics where I think actually the field has done a messy job of like these terms, model free, model based, and sometimes you just need to write down the math. And it's like bad to get too indexed on the exact semantics. Yeah.
So for this MCTS thing, so it's not used in GRPO and DAPO, right?
That's right.
So are you saying that this is an analogy of how chain of thought is done, or are you saying that the frontier labs are doing something that's not used in VRL?
That is a great question. I'll talk about it a little bit more lately. I think that there's, I would say it's mostly about the analogy. That's right. So it's not like people are, as far as we know from the literature and most science, there is not like direct use of MCTS in some of these models, but you do have, I would say, both. You do have, spending more time to sort of examine possibilities, both in serial, so in depth, and in parallel, so multiple strands being explored at the same time. And we know that there's sort of both of these things going on. Yeah.
Right, but explicitly teaching the models to go through this tree search has not led to better IQ.
That is true so far. Yeah. Yeah.
There's a really old proof in optimization that if you want to optimize the trajectory, you could optimize each small step along the way. Yeah. Richard Bellman.
Yeah.
A zillion years ago.
Yeah.
But here you're talking about a situation where you can't be sure. There are too many options, and you can't simply, by brute force, compute that, maybe unless we get to a bigger data center.
Yeah.
Is there some link between that older set of proofs and what you're now trying to solve?
Yeah. So there absolutely are lots of links, and I don't know if I want to get too deep into it. But I think like the short thing to say is like, look, the data center size isn't going to help. Chess is too big. You need to use neural network approximators for the policy and the value function. I think that's just like very clear. And then what I think we have seen is that sort of the Bellman operators, that sort of the sort of this idea about how to do learning, often is about how to do backups on the value function. This is what it's sort of coming down to. And I think what we think now is that you can absolutely do that in these value functions, and what you get is, sure, the space is too vast, but there are patterns on chessboards, and that's indeed what humans are indexing on as well. And when you do Bellman style backups with value functions, those patterns let you generalize across the space, even though you haven't seen most of it. And that's I think what we think is going on. Yeah. Okay, so then I guess like the raw result is that this putting these pieces together with the value function and the policy network together with a good simulator produce very good chess performance. And in fact, like you could basically, part of this is that you could pour more compute into it and get better outcomes, which I'll show a bit more in a moment. But this worked. Planning with an environment model really works. So it's better than just having just this value function, right? So the value function is a model of like just what's going to happen to the reward in the future, but there's this sense of like, well, can I have a more intricate model of like, the actual details of the movement of the world? And this is what was used in this work. So the next couple pieces of work that I'm going to run through quite quickly now, because I want to get back to some of the language model stuff, are places where we've relaxed that assumption. So we basically said, like, look, in the AlphaGo case, we showed up with a perfect model, which was like the actual chess simulator. What if you didn't have a perfect model of the world? Because in fact, that's most of the world, right? We do not have perfect simulators like chess engines. So one of the algorithms that we worked on is called mu0. And basically, it builds what's called an action condition model of the future policy and value. And these are the essentially like the components you need to do MCTS. And then it does not produce an explicit environment transition model. I'll talk about what that means in a moment. But in effect, it's enough that you can do this planning. So how does this work? So here's sort of another picture of the MCTS tree, right? And usually in this MCTS tree, here this link G, that would be our perfect simulator. That would be our chess engine, where I say, if I'm in this board state and I take an action, this action, it will take me to this board state. And the chess engine would tell me exactly how that works, right? Like, I play this move. Okay, well, the rook is taken. It moves off the board, like blah, blah, blah. In the mu0 algorithm, this is a neural network itself. So this link G is replaced by a neural network itself. So it's a learnable thing that you can tune up over time. And so you're sort of saying, I'll dispense with the simulator, and I'll just learn this. The other components here are you're also going to predict the reward that you would get. So all of this stuff is prediction. You're going to predict the reward that you got from this action, and you're going to predict the policy and the value function as we did before. So you're going to predict reward, policy, value, and how the environment processes. So when you play a game, this is basically, this is how gameplay works with this stuff. You sit at this board state, you build up your MCTS tree. That gives you a probability distribution over your actions, and you'll usually pick one of these ones with high probability, play the action, and carry on like this. So at every state, you're building up this tree, et cetera. And the tree is, in some sense, you can think about it like the tree is thinking in this sort of nominal, in this sort of high-level descriptive sense. So then how does this stuff learn? Well, once you've played these rollouts, so once you've done those rollouts like I just showed you, you then have some data set of like, these were the moves that were played, these are the rewards that I got, this was the outcome, these were the actions I played. And so then literally you just put this whole piece is a model. This is your data, which is board states, actions, and then you have rewards as a piece of data up here as well. But then you just train that model to make these predictions. And that's it. And then once you have that, so that's this very sort of linear model that you predict, right? once you have that, you can go back and employ it to build up these trees, right? So it's the thing that lets you basically say, well, what if I explored this action? What if I explored this action, et cetera?
So how do you get the gradient on G?
The gradient, exactly. Okay, great. Great question. How do you get the gradient on G? In this case, the gradient on G is literally the combination of the loss functions, which basically say predict reward, predict policy, predict value. And it sounds a bit weird to ask a model to predict its own policy. That might seem a bit weird, but I guess I would say, we don't use the neural network directly to produce the actions. We use the neural network to build up a tree, to do a bunch of thinking, and then we choose an action given the tree that we've produced, right? That tells us about which actions are most interesting. Yeah. So you're actually also predicting your own actions, which is kind of spooky, but makes good sense actually. Yeah.
Just wanted to clarify, you said there's no simulators, so is there something that makes sure that the model actually follows the rule of chess?
Great question. So in this work, and maybe I'll just cut to the punchline, this stuff learned to play chess, shogi, Go, and a bunch of Atari games. And in all of these, there was no information given about illegal moves. What we did in this work then was the networks really had no idea how these games worked. So the way that games worked was you would play, and if the model played an illegal move, you would lose the game. So you learned not to take illegal actions, basically by trying them and then being like, oh, that's an illegal move. And so quite quickly, the models learned look, I can't move upon sideways, right? Basically, yeah.
So my consequence of that is because the reinforcements of playing an illegal move include, then I mean you get the same feedback for playing illegal moves and bad moves, which means the model is basically exploring the rules of the game.
Yes.
The good way to play is essentially the same way because an illegal move is the same thing as bad.
That's absolutely right. Yeah, yeah, yeah. That's what's happening here. Yeah, yeah. Exactly. Okay. So then, just very briefly, what am I at for time? Okay. Oh, yeah. Okay. Well, I'm doing worse for time than I thought, but it's okay. So this, I think, is then maybe a super interesting one that ties to sort of the central thread here, which is that what we're plotting here is how many seconds or the search time you put into producing, you allow the model to put into producing moves, and the blue here is the learned model, and the sort of orange here is the real simulator. So that's like AlphaGo with a perfect simulator. And actually out to quite a fair amount of time, quite a large search tree, the learned models really learn to think about as well. And so, sorry, this is ELO here, which is basically performance in chess. So this is how well you perform. And so the first thing to say is that as you put in more time, your performance goes up and up and up. This player will basically never beat this player. I mean, that's once you're 1,000 ELO off, it's kind of impossible. Even a few hundred ELO, and it's going to be very tough for you. So this is saying, basically, as I put in more search time, as I put in more thinking time, as I build up that tree to be bigger and bigger, I'm producing better and better performance. And then this is just saying, actually, these learned models perform about as well at thinking as if I use the perfect simulator in my engine.
Why is it on top most of the time?
That's a good question. I wouldn't over-index on that. I think sometimes it's maybe there's something to that, but I wouldn't over-index on it. I don't think there's a big claim to be made there. I think the main claim is that it's about as good. Yeah. Okay. I'm actually given time. I'm going to skip a little bit and try to get back into the language model stuff and give us some time to think. I was going to talk about one other model-based algorithm that we've worked on that I think is quite interesting. But I think it's nice to connect to some of the chatbot stuff, which I feel like is, people are probably going to be thinking about and make some of these links. So let's do that. Okay, so with a lot of that loaded in your heads, like how does the basics of reinforcement learning work? How does model-based RL work roughly? Then what's been going on and what could we expect? One of the things to say is, I made this claim that like RL has driven a lot of progress in the last year on chatbots, but weren't we doing a bunch of RL for language models before that? Yes, and the answer is yes, sort of. This is mostly what we sort of did though, which was we did a bunch of pre-training, and this is the thing that everyone knows, I think, where it's like you get the whole, you download a bunch of the internet and you try and predict the next token. That's the thing that I think like everyone and their grandmother probably knows at this point. The next thing that we did was people sort of did a bit of supervised fine-tuning after that, where they basically would take a small data set of questions and answers and sort of do a little bit of fine-tuning to give models the idea of like, look, if you see something that looks like a question or a request, produce this kind of answer. And that was this supervised fine-tuning. And you can think of it as very imprecise off-policy RL. And it helps. It makes the models like actually responsive and interesting as a chatbot rather than kind of like mushily predicting stuff. And then there was another phase that people went through where they, on top of that, put something called reinforcement learning from human feedback. And basically what they were starting to do was collect human preferences on the answers. So they would say, I prefer this answer over this answer. They would build a model of that, and then they would use that as a reward. And tune on it. And this was a bit more useful, but really it didn't produce all that much more performant models for a lot of these hard things where there was really coherence and reasoning and problem solving at play. Yeah. And I'll get into why. So this is the shift in paradigm that has happened in the last sort of 12, maybe a little bit longer than that now. But this is the shift in paradigm that happened. We went from this reinforcement learning from human feedback, where it would be like, you go from a question, you immediately ask the model for an answer, right? So this is one of the funny things that people were doing. You say, just give me your answer right away, start producing those tokens. And then we would give it a reward based on human preferences, usually using a model. One of the things that would happen is that the reinforcement learning would hack those models. So they would exploit them and they would find funny ways to elicit higher reward from them that were not well coupled with what human preferences would actually be. So we call this reward hacking. It was a big issue, and it basically meant that reinforcement learning would run out of steam very quickly because you would see reward hacking. So there's two key changes that have happened, and they're really just here to see a lot of these huge performance increases. One of them is that we've sort of said, okay, before we ask for the answer from the model, we'll give it time to think. So we'll give it a whole bunch of tokens where it can just spin its wheels and try stuff and think. And this is equivalent to sort of building this, this tree in the MCTS case. And then we'll ask for the tokens, for the answer. And then we're going to start using a lot more machine feedback. And by this, I mean things like, if you're doing math, literally check whether the solution is correct. If you're doing computer programming, literally check whether the unit tests passed. If you're doing some piece of reasoning, like some logic game or something like this, literally check whether like the answer that was produced is correct. So don't rely on this sort of fuzzier human preferences, but really precisely give reward based on these. Where you have precision, use it in the reward function. And that has been a big part of
the drug. Scenarios, right? Human feedback is for moral and static subjective tastes.
Absolutely, and yeah, absolutely.
So what about? So I guess the question is, what do you do with still objective things but are harder to write rubrics for? For example, data analysis 101, you have a Jupyter notebook with 20 different mistakes.
Yes.
But it's impossible for me to preemptively write down all the verifiable rules beforehand.
Absolutely. Maybe I'll come back to this. There's a couple slides that try and touch directly on this point. Yeah, this is a very good question. Okay, so I'm going to try and very quickly take us through how we got to some of these key changes and how we got there. there was this key idea, which probably many of you have heard about, called chain of thought reasoning, which started a lot of the way that people do this in practice, where instead of asking for the model, asking the model to produce the answer immediately, to produce those tokens immediately, people started giving models examples where they say, like, look, here's an example where I give a bit of reasoning before I produce the answer, just prompting the model with these kinds of things. And so then when the model was then trying to produce its answer, it would first like spew out a bunch of reasoning tokens and then the answer. And this actually helped like kind of immediately with no reinforcement learning. So there was some sense in which you could basically say, like, before you produce your answer, just give me some reasoning. And actually, even just doing that, you saw improvements in performance. Maybe the important, this was a very easy math problem set at the time, but this jump was primarily attributable to basically just prompting these models to try and generate some reasoning. Now, that was a relatively easy math problem set, and this performance from just prompting the model kind of leveled off quite quickly. So it was basically, there was only so much you could get out of it. But it put these models on track to be able to do more if you started to learn and do reinforcement learning. So this is kind of then actually what people do in practice for a lot of this stuff. This is in practice then how a lot of this stuff works. You would take your question when you're learning on it, give it time to have a chain of thought to like produce a bunch of tokens for reasoning, generate an answer, get a reward for it, do this a bunch of times for the same question, and then from this you can basically say, hey, look, this one was good. This one produced a good answer, produced a good correct answer here, say, like this one won the game if you like. And then you can use basically policy gradient to reinforce these actions. So that's maybe the way to think about it. Like you can think about these chains of thought as a series of actions that you've taken over time, just as you did in chess games. And then you can apply exactly as we talked about before, the policy gradient to say, if this was the time that you produced a good reward, like you got the math problem correct, I'm going to reinforce those chains of thought, reinforce those kinds of answers. This is how you win. Back to a question that was asked earlier about MCTS. Another thing you can do is that you can start to employ these what are called parallel rollouts to produce even better answers. So you can imagine that if I build a model of this reward, so I can basically predict what reward I'm going to get by looking at the question and the answer, I could roll out a bunch of these. And let's say it's a case where I don't have the reward function. I'm not in training mode. I'm actually interested in the answer. I can then query my reward model, something like my value function, and sort of say, which of these answers is likely correct, and then basically choose the one that I think is most likely correct from here. So this is a way to basically start to use both serial and then parallel sampling to produce better and better answers. And this is part of what goes on in especially some of the biggest models, which sit there and think for minutes, right? You're basically sort of having a bit of like, sure, you do these long rollouts, but you can also do a bunch of parallel ones, and the combination of those gives you even better answers. They're just very expensive and time consuming. So this is just to give you a sort of sense of what this looked like in the DeepSeek paper, which I think is like a great paper, a great reference paper for this. They really sort of like trimmed down and made clear some of the sort of stuff that was going on conceptually. These are just the learning curves, and this is when you go and basically do learning as I've described it on these couple slides. These are the learning curves, and then coupled to that is like we go and look behind the scenes at what's happening for these models. What's being plotted here in this paper this is the time steps of reinforcement learning. So this is how reinforcement learning going on in the x-axis. And this is the average length per response. And by length, I mean the chain of thought length before you produced your response or answer. And this is starting down around like, a few hundred. And basically has grown up to, I don't know, about 10,000 there. So this is like what's happening then. For this tiny little answer you might get from a math problem, there's like tens of thousands of tokens that are being produced behind the scenes. And that's sort of like fairly common, just like fairly part of what's going on now when we query these chatbots all the time. So a lot of the action is sort of in the thinking behind the scenes. Yeah. This is happening both during learning and evaluation time. Yeah, that's right. So, and in fact, like this is maybe the coupling here was there was this period where people would sort of say, well, I can do this chain of thought prompting and get the model to spend a little bit more time. But actually, to do the when they did the prompting, they would get it to spend like a couple hundred tokens. But the learning actually is what elicited it to sort of spend more and more, and for the models to realize like, oh, I can actually just spend more compute and more compute in order to get a higher probability of this answer. And so I'll do it. Yeah.
What was your take on training the reward model to operate with chain of thoughts too?
Yeah, good. Great question. And that is related to, I think, the earlier one that I said I would get to. And I think we have 10 minutes now. Is that right?
Including the question answer.
Including the question answer period. So I actually want. Oh, actually, I'm actually in a good spot. So we're going to be great because we're going to end on some of these questions. It's perfect. So I wanted to say a couple things about MCTS and chains of thought, and then end on this question you mentioned. So MCTS, like you build up these trees, and that's like a very intuitive thing. And these chains of thought where I just have a linear rollout are kind of weird. Like, you know, it seems like maybe not as good because you're not really building up sort of like some map of the future, if you like, right? But because of the way transformers work, there's a sense in which actually these models implicitly probably have something like a tree that they're building up behind the scenes. And that's in effect because like within the chain of thought, attention mechanisms can link the thought now back to this thought at this time, and this one back to this one, and so on. So these attention mechanisms really let you build up something like chains of like trees in a linear chain, which is kind of remarkable and has a bunch of advantages. Yeah, that's this point. Attention can look up past ideas and iterate on them or avoid them, right? So you can like look them up and be like, well, I already tried that, so I'm not going to try it again. It was a terrible idea. I'm going to go explore a new idea in this chain of thought. So I just wanted to make that link. It's kind of funny to think about these linear things as trees, but there is a way to do it if you think about attention. Then I'm going to come to this question about fuzzier problems, because I think this is like key for the future and key to like what I think is going to like unfold from this point forward is a couple of these pieces. So simple math and execution feedback. Execution feedback, I mean things like checking unit tests, checking whether you pass unit tests for code. We've made a huge amount of progress here, basically by saying, hey, you're allowed to spend more compute, and now I have a really good reward function. And putting those two pieces together has just driven like crazy success over the last year. I mean, yeah, crazy success. I'll mention one piece of that in a moment. But the question is, I think it was asked here, what about these cases where there's more sort of aesthetic judgments or like fuzzier judgments? Like, how do you work with those? People really spent a bunch of time on these extreme like aesthetic judgments at first, and it was probably a mistake for the field in a way, in the sense that people were sort of over-indexed on that for RL. I think actually what I think we're going to see now and what we're beginning to see is a movement from here in that direction towards the fuzzy direction, and people are going and getting reward functions where we have like real good expert agreement, or like 90% of humans would agree on this, and capturing that information in a reward function, and once you've done that, then you can go and use it in learning, right? And so that's the sort of process that we're seeing in that direction. Is that a question?
Yeah. So can you hold it until the end? It's more of a conceptual question.
Okay. Then let's hold it for one moment. The other one that I think that came up was this thought about, hey, what if we could use this idea for the reward models themselves? And indeed, I think that is the other thing that is starting to happen. People sometimes call these grading models. So you would basically, instead of just putting in the question and the answer, I'd maybe put into the question the rubric, a rubric like we often do for TAs in schools, an example like good answer, and then the answer from the model. And then I'm going to let the model, this reward model, think a bunch before it produces a grade, right? So I'm actually going to like, instead of just having the reward models very quickly blindly output a reward, they're going to be able to think deeply before they output a reward and use that. And so I think this is going to be another big driver of what we'll see in the next few years. And then I think just to sort of like round that out, end on it, one of the recent successes that we had with this specifically was around the International Math Olympiad. These are hard problems. I don't think on any given day I would do better than a bronze. This model in 2024, the silver medal was won with neural networks using formal statements of the math, which was like a lot of human effort to formalize them and then approached. In 2025, we had a model win gold, engaging directly with the informal English problems. And I think the important thing to say on this math stuff was it was not simple math problems. These were problems that required proofs. And it's a funny thing to say, but proofs are actually very blurry, and you do not have precise checkers for proofs except in the formal case. So this is a case where some of this fuzzier stuff was actually coming to bear, and we can actually make some progress on these things. Okay, I think I'm gonna round out there and just take some questions. There's a huge number of people who've been behind this work. Sorry about skipping some slides. Hopefully I've managed to connect roughly where folks are here. Yeah, please.
Yeah, so I'm going to echo some of the initial reasons why neural networks were so niche in the first place in cognitive science. But my question is, so even at the end with your most complex models, it seems like the action space is still pretty low level. Like you're still looking at the next step. Why not build into your models a little bit more, and you're basically allowing things to emerge. You're allowing these strategies, for instance in chess, to emerge naturally rather than telling it these strategies. Why not tell it the rules? Why not like train on that at a higher level, higher level of abstraction beyond just what's the next move I can take?
Yeah, so I guess I would say in some sense to the why not, I would say I think that is precisely what people are starting to do. So when the sort of era of game playing in RL was happening, there was like we just did not have models that could do anything like read an instruction manual. But actually, it's very reasonable now to sort of basically give models an instruction manual, and they're still pretty imperfect, but like they can grok an instruction manual and use it to sort of begin, to take strategies in some direction. So I think that just is happening.
The way that train is still on next step, and you're letting it emerge, like because you need so many steps, right? Like you're training millions of steps. Can't you cut down on that training if you gave it some of the things that we use to cut down our own training?
So there's a lot of things to say about this. I think that this like 10,000 tokens, tens of thousands of tokens. I do think that people will find ways to cut that down significantly. I think that one of the things to comment on here is that actually the reinforcement learning algorithms that people have applied thus far, things like GRPO and so on, are relatively simplistic. And I think we know basically that there are better algorithms out there for reinforcement learning. Some of the pain is just like applying these algorithms at scale is hard. So even doing the simple stuff at scale is difficult. So I fully anticipate that the number of tokens that will be used will drop. Even so, I think you could ask like, is it sensible or sane to be asking models to think step by step in sort of like English tokens or just like any kind of token space? And I think that's a great question. There are some folks exploring the idea that instead you just have sort of a latent space, and indeed it processes, it would process, but there's no necessary attachment to a specific token space. I think the jury is out on that. Like we don't know where the research will fall. One thing to say that is a little bit funny and weird is that, if you look at this basic setup, this basic picture of like question, chain of thought, answer, you can begin to see all kinds of weird, crazy stuff in the tokens that the models develop in this chain of thought space, right? Like they can develop their own kind of kooky way of talking to themselves. And in fact, we think that if you kept the reinforcement learning going longer, those might disintegrate to the point where it would not really be understandable to humans. And then really, like what's really in some sense going on, or part of what's going on, is that it's just all the activations in the transformer that lie behind those tokens. So the tokens are kind of like almost this surface level part of the computation, and there's tons and tons of computations that are just going on in the transformer activations. So I guess I wouldn't over-index on the, yeah.
So I have a question. So you mentioned that one of the problems with the chain of thought reasoning is that they have no clear backtracking and no separation of attempts. I'm wondering if there has been any attempts on adding some like graph-based learning or some explicit program for the model to learn some clear path in their chain of thought reasoning, so that we can have clear separations and don't have confusions within the model.
Yeah, so that is an amazing question. I didn't even mention it. So yeah, I guess you indexed on this, right? So one of the potential cons of using this sort of like these linear ways of thinking about the future is that there's no clear backtracking. You could potentially get things very muddled up in these long chains of thought, and maybe the attention will sort of start to have trouble indexing on exactly the pieces of information in the past that are desired or wanted. I think that there are people trying to do exactly what you said in the literature. I don't know if I think we've seen anything convincing. And I think actually the jury is out in a way as to how much formal structure you'll want versus these very mushy things like transformers with attention. My guess is that in general, we will end up with solutions that look closer to these like mushy transformery things that have enough flexibility, and probably will end up mostly on that end. The trend has just been, if you have enough data, if you can do enough learning, more flexible learning devices tend to perform better in the long run. And so that's why my guess would tend in that direction. But in terms of exactly how much structure will be injected and the right balance of these things, I think it's anyone's guess about where precisely the balance will be. And so like just to connect it for other folks, it's like, in MCTS, there's this very specific, explicit structure with a specific, explicit way that you traverse the tree, you back up values and these sort of things. Whereas in these chains of thought, it's kind of just like a big mush that you like, it learns to attend where it wants to. It's messy.
Yeah, first of all, thank you for a really clear and beautiful talk and really exciting work. I wanted to sort of go back to your roots in a way where you started, which is a lot of the concepts here came out of cognitive science,
yes,
psychology, neuroscience, neural network itself, synaptic weights, reinforcement learning,
yes,
behaviorism, and it's really amazing to see those ideas scale from cognitive science to applications like this. And I'm wondering, just, I don't know, it's a speculative question. Are there other kind of secrets or powerful forces hidden in us that could be exciting to incorporate? I'm thinking from a learning perspective, there's work on like testing effects. So like quizzing yourself is a great way to learn.
Right.
Or spacing, or in decision making, how we both learn sort of general value, but we can also use individual episodes to make decisions. Like, how do you see the frontier of the interface?
Yeah, the frontier of the interface. I mean, I think like this is it's a very funny business, right? Because I think that the flow, especially at high levels, is kind of there and continuing to happen all the time. Like look at it, like this was like a perfect example. This is like a very high level like cognitive idea. It's just like, I'm going to try and get the model, before it spits out an answer, I'm going to try and get it to give some reasoning before it spits out the answer. It's like a very high level cognitive strategy that was employed to produce like markedly better effects. And so I think these things are all over the place. And then the thing that's like kind of weird and painful is like, it's sometimes hard, it's just hard to predict when you're going to see big wins from the transfer. And to make things really work at scale, you kind of need to combine those insights with, just extremely good engineering. Like the folks who did this, I did this is like some folks at Google, and at Google, like extremely good engineers, right? So it's like often the people putting this together, it's like a coupling between an interesting high level idea with like some pretty powerful engineering. But it continues to happen all the time. So I think that the thing that I've become a bit more skeptical of is like, here is like a very clear, here is a very precise circuit or something in the brain, and I'm going to go and try and implement it, and I'm going to bet that like this is going to produce better AI. This I think is like rarely the case, and I think is like unlikely to pan out almost all the time. But the transfer is happening still very regularly. So it's a funny mix.
On that note,
yeah.
I think we'll take all the other questions offline and thank the speaker. Thank you.